Okay, let's get started. Firstly, thank you all for coming. I can't believe this many developers have turned up for a talk about philosophy. I hope you read the abstract. So, what we're going to talk about for the next hour is philosophy and architecture. And for the last couple of years, I've been working on a PhD in complexity science and software design. And in doing that work, I've come up with a brand new way of thinking about software architecture and a completely different way of doing the work that we do when we design software systems. And a lot of people ask the question, how do you do that? How do you come up with a completely different way of thinking about these things? And the way that you do that is that you go right back to the base of how do I view the world? How do I solve problems? What do I think is a problem? What do I think is a solution? And so for the next hour, we're going to look at what is the relationship between philosophy and architecture. And you might think that it's very, very far away from software development. But by the end of this 60 minutes, you'll understand the impact that your philosophical thinking has on the way that you design systems. So we'll start with a paper that was published in 2016 by Ralph and Tim Perrow, where they investigated the decision-making of software engineers. And they asked a very large number of software engineers, how do you make decisions? Whenever you have a software architecture and we see that you have 3 components solving a particular problem, why not 2? Why not 4? What lies behind that decision? And the almost unanimous answer of software engineers is, we don't really know. We're not sure how we make these decisions. We know it's right, but we're not sure how we arrived at that decision. There's a lot of vagueness about how we arrive at a particular design. And this causes us to ask the question, what is it that we do? What is it that architects actually do when we make decisions about the structure of a software application? There's 2 parts to that question. What is architecture in theory, and what is it in practice? And I always like to use this example when I'm talking about the difference between theory and practice. And so you'll see in this picture here a 14-year-old boy called Taylor. And Taylor's father was a physics professor. And Taylor took some of his father's textbooks to his garage, and he built a small nuclear reactor, which kind of became a big deal for the local authorities. Now, whenever a 14-year-old can take some textbooks, go to a garage, and endanger a small town, then that's a pretty good sign that theory is pretty close to practice. That's a good sign. Now, I want you to imagine instead if Taylor's father, instead of being a university physics professor, had been an enterprise architect. And Taylor had taken some of those books to the garage, what would he have built? At the very best, a small fire. Or perhaps better for Taylor, he would have gone out and done normal teenage things. Why is this? Why is there this massive gap between our theory and our practice? Well, it looks like this. Whenever an architect represents an organization, which is a living, breathing, moving human system, the representation tends to look a little bit like this. At the highest level here, we have C, which stands for capability, which is how architects in the first movement start to break down an organization. It's a set of capabilities like sales or marketing or manufacturing. And we say that every capability is made up of a bunch of processes. And every process has a bunch of supporting software components. And when we look at this kind of diagram, what does it look like? It looks suspiciously like a circuit board. Now, why would we choose to map a human, complex, constantly moving organization as a circuit board? Why on earth would we choose to do that? It's because that's how we see the world. That's the way we've been trained to think. What really happens, what this thing represents, is a human system. And we have this blue character here inside our human system, which has people and groups of people and organizations and some software components. And what happens is This blue character wants to do something in the world, and they stumble around trying different things until eventually one day they reach the market up here that they wanted to reach. And once they've done that, they have a business, a successful business. And what they do is, then the enterprise architects come in and they take these white arrows and they map it to this kind of rigid circuit board-like structure. And they say, here's your architecture, we're done. What they don't see are these green arrows, and these are things that the British researcher Ralph Stacey calls hidden transcripts. They're the hidden relationships, the hidden thoughts, and the hidden groups that exist in a social system that you can't actually capture or see or write down because they're constantly moving and constantly changing. These things cause so much problems for us, we had to move to agile ways of development to cope with them. And what happens is that these green arrows, they pull on the network, they pull on the system, they influence it, they change it. And then all of a sudden on the periphery, new technology and new actors pop up. And there's a new way to solve this particular problem. And when that happens, we call it disruption. And when that happens, the white arrow architecture that we've put years of work into collapses completely and actually becomes a problem for the organization. The obvious example of this happening in the real world is Blockbuster, which in the United States had a very successful business with their white arrows where they hired movies to people on the weekends. And they made all their money on late fees. And they didn't see the green arrows, which was the seething hatred that was building up in their customer base because they constantly, every Monday, had to pay a whole bunch of late fees because they never left their movies back on time. Netflix saw this and popped up. And all of a sudden, there was a new way to reach this market. Blockbuster had the opportunity to buy Netflix, but they passed over it. By the time they realized what Netflix were going to do with streaming, they went back to their architects and they said, can we fix this? And their architects said, yes, but it'll take 18 months because we have this big, heavy white arrow architecture. 18 months later, they were bankrupt. That's what can happen when you view human organizations as these stiff circuit board-like things. So what is architecture in theory, then? In theory, we think that we work in a very structured way. We believe that we're scientific because we studied computer science. We believe that we're mathematical because computer science has its roots in mathematics. And that we're analytic. And that we're rational. And we believe this of ourselves, that we're scientists, we're engineers. I don't think this is strictly true. Architecture in practice is sheer, unadulterated panic. We don't know what's happening. When we think we know what's happening, everything moves and changes. And it's very, very difficult. But we still pretend that we're using some kind of theory. When a junior architect comes to you and says, how do I do architecture? You say, read this book and read this book and read this book and this blog and do this thing. And if they ask you, do you actually do the things that are in this book? We know that we don't, right? But we pretend that we do. And the consequence of that is that we struggle to articulate the basis for our decisions. So basically, architecture is mostly lying. There's a very interesting article that was written in 1986. It's called A Rational Design Process, How and Why to Fake It. And this article, when I first discovered it a few years ago, made me giggle because it starts off by saying, look, there's no structured, rational way to do software architecture or software design. It's always a mess. It's always chaos. But the article goes on to say, it's worthwhile lying to management and pretending that you're doing things in a rational, structured way. Otherwise, they get very nervous. And so this isn't just my thinking. This article also says the same thing. And I thought that this person was being sarcastic, and then I looked at the name. The author of this article was David Parnas, one of the most important researchers within software engineering in the last 50 or 60 years. That's where we're at. And so the question is, why are we like this? And that's the question we're trying to answer here today. Philosophy gives us a tool to help us question our assumptions about the world. It helps us ask deeper questions than the everyday design of components and systems. We want to ask, how did we get here? Why do we think like this? What do we actually believe about the world? And in order to do this, we'll have to look at a couple of the problems that we see with software architecture today. The first major problem, the biggest problem in software architecture, is the problem of time, change, and uncertainty. Architectures, we draw them as static two-dimensional diagrams. We say, here's my architecture, a bunch of components connected to other stuff. What we don't represent is the fact that that architecture will not look the same in 6 months or a year or 2 years. It will constantly change over time. We don't capture that. And the reason that we don't capture that is because we don't actually know. Nobody actually knows how things are going to change over time, not even our stakeholders. And this makes it very, very difficult to do architecture. Another issue that we have, which is a philosophical issue, is that we don't really have a unit of architecture or a unit of software engineering that we can gather around. What does that mean? Well, when you have a unit, when you have something that we all agree on is true, then you can build a science around it. And the Greeks realized this 2,500 years ago. And they started to say, what is at the core of all this? What is the unit of the universe? And they came up with some crazy ideas, like it's earth or fire or wind or water. And those were reasonable starting points, actually, when you look at it. Eventually, physics arrives at the atom, and that came from a Greek called Democritus. And the atom becomes the unit of physics, and we can build a whole science around the fact that everyone's in agreement that there is this thing called an atom. Although some people on Twitter were disagreeing a few weeks ago, but we'll not dig into that now. For a lot of us who've studied mathematics, the Newtonian particle becomes the unit with which we assemble around and build a science on top of it. Chemists have the molecule, biologists have the cell, and this allows them to be successful, to communicate with each other and build a base. In software, we've been having a bit of a journey. We're not quite sure where we're at yet. We started with the machine. We were very tightly coupled to that. Dijkstra saved us. We moved to punch cards, procedures, modules, objects, which has entertained us for decades, services, and then eventually we move into business concepts like processes or features or functions, patterns. And the chances are, if you've got a group of software architects assembled around a problem, they're all working from a perspective with a different unit. And this causes lots of friction and lots of weirdness and lots of disagreement. And we're still in the Greek phase of earth, fire, wind, and water. We're not entirely sure what we're about yet. In 1962, a philosopher of science called Thomas Kuhn wrote a book on the structure of scientific revolutions. And he talked about how scientific ideas change over time. And he said that a scientific idea will exist for a certain amount of time and people will assemble around it and they'll build knowledge on top of it. And what will happen is that the scientific idea will start to suffer from some anomalies. There will be things that it can't explain. And as that starts to happen, people start to doubt the idea. And some people desperately try to patch the idea and keep it alive, and they become very defensive of it. But after a while, the idea collapses and is replaced by something new. And that's called a paradigm shift. And in science, we have these huge paradigm shifts every couple of 100 years. In software, we have these huge paradigm shifts every 6 weeks, it feels like. It's constant, and it's exhausting, and it's a sign of where we are. All of these problems are philosophical problems. They require a different way of thinking. You cannot code your way out of these problems, and we have tried to do this. And so, I'm going to have to give you a little introduction to some basic ideas in philosophy. I usually describe myself as a software engineer who got lost in the philosophy department of the library. So if you're watching this on YouTube and you're a proper philosopher, please don't do that comment thing, okay? So 2 very important concepts to us, and an important concept to the history of Western philosophy, is the difference between essence, and essence is the core of something, the way that we think about something, the way that we group things, and appearance, which is how it actually appears to us, how it behaves in reality. And a lot of Western philosophy is about noticing the differences between these two things and trying to make the differences go away. And a concrete example for us is that the core, the essence of something, is the requirement specification. We've tried to boil it down, we've tried to capture it, we've tried to describe it in detail. And then, of course, you have reality, which has absolutely nothing to do with the requirement specification. And the difference between these two things isn't just something that happens in software, it's a problem that's been around since ancient Greece, and we don't really know how to solve it. In ancient Greece, there were two huge thinkers that shaped the way we think in the West today. The first one is called Heraclitus. He's the guy with the white hair and the beard who looks like a senior software engineer. Heraclitus said that the world is made of fire. Everything's burning. Everything's moving. There is no things. It's just an illusion. Everything's moving past so quickly, and we're trying to make sense of it that we think there are things. Heraclitus is famous for the phrase, "No person ever steps in a river twice because they're not the same person and it's not the same river." You've probably heard that phrase before. And that description of the world is probably feels very familiar and comforting to you as software engineers. This is the way our world works. Everything's moving past so quickly, we keep getting it wrong. On the other side of the coin, we have someone called Parmenides. And Parmenides is the guy here who looks more like a product manager. And Parmenides said that everything is still. Nothing is moving. Everything in the world is still. And the reason you think it's changing is because our brains are a little bit funny and we can't cope with the stillness. So we make up this change. And these two thinkers were in direct opposition to each other. And they were both a big influence on Plato. And Plato is the founding father of how we think in the West. And Plato chose to side with Parmenides. He chose to side with the fact that the world is still and that we gain knowledge by gaining knowledge of the things that are actually still, the essences at the core, when our brains stop being confused about what's actually happening. And that decision by Plato might seem a very, very long way away from software engineering, but it affects every decision that you make in your architecture today, which is pretty cool and pretty scary. So at this point, you might want to ask yourself, what is my philosophy? What is my philosophy of software engineering? And most of the time, we won't be able to answer that question because we've never been taught how to answer that question. We spent all our time doing cool stuff with algorithms at university. And what actually happens is, it turns out that we all have a default philosophy, which we've never been taught how to question, and we've never asked about it. And that default philosophy comes from our university professors. And we have to ask the question, where did we come from as architects? And this is where we come from. You should recognize most of these names on the screen, hopefully. These people all had one thing in common. They were, more or less, they can be described as positivists. They all have a similar philosophical view of the world. What does that mean? Positivism is a school of philosophical thought that believes that the universe is clockwork, that the universe is just a big bunch of gears, and if you figure out what way they're linked together, then you'll know which ones to turn in order to make things happen. They believe that there are independent, objective laws that govern not only the physical things around us, but also our society and our minds, and everything can be mapped, like circuit boards, like chips. This way of thinking is very much based on logic, and without this way of thinking, we would never have had computers. This is what gave us logic, this is what gave us Turing and von Neumann, this is what gave us the computer. But it also gives us the software crisis because of the difference between essence and appearance. There is another way of thinking, which we can loosely group and call interpretivism. And so where positivism looks for laws that govern the universe and uses scientific method to investigate social systems and believes in observation, experiment, and logic, interpretivism allows there to be different views of the same reality. And it rejects the scientific method for social systems on the simple premise that it has never worked. And interpretivists will say that knowledge isn't something out there that we discover using the scientific method, but knowledge is something we come to through ideas and debate. And the fact that you're all here listening to me talk about ideas is proof that this is how we learn. Otherwise, you would all be back in your offices doing experiments, which we don't do. And so there is another way of looking at the world. The problem is that we come from the positivist side and we think that that's what rigor is and we think that that's how you should solve problems, but we actually act like interpretivists. And there's a problem there, there's a dissonance there. Now, every single one of us, because of our university educations, has a default philosophy. If you haven't thought deeply about these questions, you're probably going to recognize how you think across the next couple of slides. The first thing that will appear in your default philosophy, if you start scraping at how do I see the world, is a way of thinking called essentialism. And this comes directly from Plato. Essentialism says that there is a core essence to everything. And Plato believed that there was a heaven somewhere, a heavenly realm. And in that heavenly realm, there were these ideal forms. So somewhere in that heavenly realm, there is a perfect cat. And every cat on earth is just a crappy copy of that perfect cat. This is what Plato believed. And he believed that wisdom was gained by getting closer and closer to understanding what the perfect cat is. And when I tell you that, most of you are probably thinking, what a silly idea. But you know, this was 2,000 years ago, so it's okay to have silly ideas. I give you object orientation. Object orientation is exactly the same way of thinking. I have this perfect class, which I've described, and all these crappy little objects, instances executing in reality. We've taken these rather strange ideas from ancient Greece, and we've turned them into the base way that we address the world. If you do enterprise architecture with something like TOGAF, you'll find things like architectural building blocks, solution building blocks that play the same role. Patterns can also play the same role. Now, that's fine when we're talking about cats, but when you apply this kind of thinking to larger systems that have lots and lots of different things in them, you end up applying a new way of thinking, which we call structuralism. And structuralism is about the ideal structure of something. And so when you start drawing lines and boxes and relationships between things, you're engaging in something called structuralism. About 100 years ago, some people thought that there's a structure in our language that reflects the underlying structure of reality, and they started looking for that. And those ideas were pretty quickly discounted, but they still turn up in software engineering in the form of requirements engineering, where we try to find reality behind the language that our stakeholders use. And some approaches, like domain-driven design, will go even deeper and try to find that structure in language that represents a real structure, which is the essential form of our organization. A third thing that you'll find in most software engineers is a naive idea of something called cybernetics. And cybernetics is a set of ideas that was developed in the 1940s by a mathematician called Norbert Wiener. And he believed that that a machine consists of feedback loops, and you get control through controlling these feedback loops. And he started to see feedback loops in animals and people and in our society and everywhere. And this led to a way of thinking where we've seen our society as a machine, as a set of interlocking feedback loops. And this led to us thinking about things as machines. Other philosophical ideas that you all carry that are important is causality. We see social systems as machines, and we believe that there's an if A, then B relationship between things in a social system. Turns out it's not that easy. We also believe that there's causality in structure, that if you reorganize your company, you'll cause a different future and you'll be able to control that. And that turns out to be exceptionally difficult as well. And the worst kind of causality is rational causality, where if you get a bunch of managers in a room and they decide on a strategy, then that's what the future is going to look like. We cause the future by having strategy meetings. Turns out that doesn't really work either. In real-life architecture, when it comes to causality, stuff just keeps happening, and we have no idea why. This all collects into one set of behaviors that we use as software architects, and that is models. Architecture is all about taking these ideas, structuralism, essentialism, machine thinking, simplistic causality, and turning it into a model. And what we actually do is we take reality and we cover it up with models until there's nothing left of reality and we don't have to deal with it anymore. And for some people, that's incredibly comforting. Now we can just sit in the basement and show each other pictures. We don't have to think about the reality behind it. There is a philosopher who was active in the latter part of the last century, a French philosopher called Baudrillard. And I've been told by some French people that that's definitely not how you pronounce it. And Baudrillard wrote a book called Simulation and Simulacra, which talks about this exact problem, that we create these models of reality and we start to live through the model instead of the reality that's there. And this book, this picture might be familiar to you because in the movie The Matrix, which I'm assuming most of you have seen, though I can see that some of you weren't born when it was released, whenever Neo goes to find his contraband, he has a hollowed out book and he has his phone and some other stuff in there, and that book is Simulacra and Simulation. The movie The Matrix is based on this book. And Baudrillard talks about how we're losing touch with reality. We're living our lives through television, which is a mirror of reality, but it's not quite the same thing, and we're getting a little bit confused. And a lot of times, you'll hear architects being accused of living in some kind of ivory tower disconnected from reality. And it turns out it's not an ivory tower. We're actually in the matrix, and it's the matrix of our own making. And as soon as I tell architects and developers we're in the matrix, they all say, well, I must be Neo or I must be Trinity. You're not. You're actually the architect. And the architect in this movie looks exactly like Norbert Wiener, the guy who said that society and people were just feedback loops of machines. And that is not an accident. The people who made this movie knew their philosophy. They knew what they were doing. You can tell that this guy is a real architect because he promises utopia in version 1. And it doesn't quite work out like that. And when it fails, instead of changing his mind, he just tries to patch it. He says, it's broken, add the oracle. It's still broken, add Agent Smith. It's still broken, add the 1. And it just keeps going. The reason that the system fails is because he fails to take into account that human beings have emotions. That's something that we regularly do in our industry. Neo falls in love and the entire system collapses. That's what happens when you have these green arrows that you can't see. And of course, he creates this massive model that obscures reality so that no one actually knows what's real anymore. And so what we have to do is get out of this matrix. And how do we escape the matrix? A lot of times when we talk about architecture, we say that what we're experiencing now is complexity. And this word is massively overused, and my studies have been within complexity science because this is what we think we're experiencing. And some people think that the way to get out of complexity is to suppress it. Let's get rid of it. We just encapsulate, whatever that means. Or we say, that's never going to happen, Yagni, we don't need to think about these things. Some people think that if you just keep iterating, you'll get out of this complexity. And that can be very tiring. And some people believe that you have to go back to the scientific method, to positivism, and design experiments and run those experiments. The way out of complexity in the past has always been the same. You need new concepts, new ideas, and a new philosophy. And to have a new philosophy, you have to break out of the old way of thinking. And that's the challenge that we stand in front of today as software engineers. If you think about the huge scientific changes that allowed us to cope with complexity, they didn't come from experiments, they didn't come from iteration. The reason that we have most of the engineered things we have today is because Isaac Newton allegedly got hit in the head by an apple, and he made a jump, a new concept. Darwin was staring at a bunch of finches when he realized that, there might be a different way that things work. And Einstein's idea of time also came as a new set of concepts, a new kind of ideas. Every time we develop a new set of concepts, we conquer complexity. We don't conquer it by tinkering at the edges of it. And I'm going to give you a set of new philosophical concepts that you don't have to adopt, you don't have to believe in them, but it's a different way of thinking about the world than the default philosophy most of us have as architects. And those three ideas are process, criticality, and difference. So whenever we focus on the thing, whenever we try to identify what is the perfect ideal cat, what does it look like? What we're doing is engaging in something called substance philosophy. And substance philosophy comes from Plato and Aristotle, and it's all about focusing on the thing. What is the thing? What makes it a thing? What makes another thing not this thing? What are the boundaries between them? And there's another way of thinking, and it's called process philosophy. And process philosophy is very much Heraclitus' way of seeing the world. Everything is moving, everything is changing. And even we are changing as the things are changing, and the way we think about them is changing at the same time. It's a completely different way of looking at the world. And one of the questions we ask is, how do we gain knowledge? And so from the Platonic way of looking at things, from substance philosophy, we gain knowledge by looking at things, putting them into categories and putting them into little boxes and saying, this is a cat, and this is a dog, and this is a sheep, and this is an object, and this is a service, this is a load balancer, this is a test. This is how we gain knowledge, and we learn these things as facts. There's a different way of learning that we use as architects. And it works like this. I've just moved house. I've moved to a new town. And I want to go for a walk. But it's a new town, so I don't know where I'm going. So I go to Apple Maps and I pull up a map. And I plot a little route. Those are car times. I'm not lazy. It's a longer walk than that. And I say, this is the walk. And this representation of the walk is Platonic. This is an ideal form of a walk. This will describe a walk in any part of the world. But as a source of knowledge about that walk, it's pretty useless. And so the first time I take this walk, I have my phone in my hand. I'm very nervous about getting lost. I walk around and I make sure that I'm taking the right turn at the right time. And all my focus is on not getting lost. And this representation has done its job. The second time I take this walk, the walk will not be the same. There will be slight differences because things are changing in the environment and because my perspective of this walk has changed. And I notice on this particular path, there's a lot of shade. And I live in Sweden. That means there's a lot of mosquitoes. So I don't want to go there. Now I have knowledge based on that small difference between the repetition. I take another walk on a different day, and I realize that in the winter, on this particular path, no one puts any sand or gravel out, so it's very slippy and it's very dangerous. So I don't want to walk there in the winter, and that's another piece of knowledge that comes from observing the small differences every time I repeat this walk. And then I realize that if I leave at a certain time in the summer, I get to experience this view, this sunset. And I take lots of walks, and I learn that some days it's maybe better not to just take the walk at all. And I learn a lot of things. Every time I repeat the walk, I notice small differences from my previous experiences, and those small differences add up to solid knowledge about this walk. Now, we have a problem in software architecture. Sometimes we believe in things, and everyone believes in different things. And you can meet two architects with two completely different sets of beliefs about what tools they're meant to use. And the strange thing is that both of those architects, if they're good architects, will succeed, even though they have a completely different stack of tools and ideas to build their architecture. And that's confusing, because it means we can't answer the question, what is the best stack? What's a good stack of tools? What's actually happening to these architects is that the tools they use don't actually help. They don't deliver anything. All those tools are doing is that they are triggering walks around the problem over and over and over again. So you think you're doing requirements, and then you think you're doing risk, and then you think you're doing patterns, and then you think you're doing test-driven design, and then you think you're doing something else. All you're doing is walking around and around and around the problem until you build enough knowledge to know what's actually going on. And this is universal to every architectural process. You could say it's an essence of architecture. And the third thing, these ideas were written about by a French philosopher in 1968 called Gilles Deleuze, which apparently, according to my French friend, is not the right way to say that either. The third thing, and this is critically important for architecture, the third concept is the concept of criticality. Criticality is a property that a complex system has when that allows it to survive things that it hasn't been designed for. So your immune system has criticality because it can defend you against diseases that aren't in its design, that aren't in its specification. It has flexibility through the number of components and the relationships between those components. We are critical beings. Our societies have criticality. Forests have criticality. They can repair themselves. They can cope with unforeseen circumstances. For programmers, their goal, and when you've gone to university and learned computer science and programming, your goal will always have been correctness. This algorithm has to be correct, this function has to be correct, this has to work in a specific way repeatedly. The goal of a programmer is correctness. That should stay. But the goal of the architect is never correctness, because you can't be correct in an environment that's constantly moving. The only thing you can be is critical. And that's a completely different idea. It changes entirely how we think about software. And so what we're doing is I'm giving you a bunch of new concepts that will help you to navigate the complexity that architects experience every day. Process instead of substance, criticality instead of correctness, difference instead of essence. And this is an enormous philosophical shift. I'll give you an example of the way that this works. What we're actually doing is we're allowing our concepts to be destroyed. So I'm building a system, and I start out with a concept called customer. Customer has a bunch of properties. It has a name. They have a name. They have a social security number. They have an address. They have a credit card. This is my customer concept. This is the ideal customer for our business. Then we take a couple of walks and we realize that there's differences. Suddenly I have a business customer, and a business customer doesn't have a social security number, they have something else. And a business customer doesn't have an address, they have lots of addresses and lots of opinions about which address we should use for particular orders. And business customers don't have credit cards because they have invoice functions. And your customer object suddenly blows up. It's no good anymore. And so you might think, well, we'll update it, and we'll say, if it's a person, then they have a social security number. If it's a company, then they have a company number. Then we get a different customer, a foreign customer who doesn't follow any of these laws, and we have to change everything again. And then we get this demand to be a one-time anonymous customer where you don't get to know anything about them, but you still have to serve them in some way, and the concept collapses again. If you ignore these conceptual collapses in your architecture, you're going to constantly be chasing your own tail, and your architecture will suffer, and you'll end up patching things in the way that Thomas Kuhn describes. So when our essences and appearances don't match, what we do is we speculate, which is a fancy word for we make stuff up. Speculation leads to a lot of noise and a lot of nonsense. And if you're a positivist, there's no tolerance for noise and nonsense. But it turns out that noise and nonsense and truth are very hard for us as software architects to tell the difference between. And so this is an important part of how we learn. And using process difference and criticality allows us to make that speculation useful. Now, the ideas that I've come up with, and some of you might have seen the talk from NDC last year, is based around the idea of a residue as a unit of software architecture, as a way of capturing time, change, and uncertainty in our architectures. And it describes the architecture across many different timelines that we discover through this architectural walking. We just make these things more explicit. And it embraces speculation through the use of random simulation. So rather than asking people for requirements, we just throw lots and lots of potential requirements at the system, whether they're true or not. And this gives us, with a statistically significant result, a better way of building architecture. This requires a shift in how you think if you're a programmer. Programmers use something called linear thinking. Linear thinking is about direct problem solving. It's mathematical, it's concrete. Your focus is in getting correct answers. And it's the key skill for a software engineer. If you can't think in a linear way, you're not going to write good code. As you move to architecture, you need to think in a different way, and this is called lateral thinking, and it's vague and it's fluffy, and it's asking what if and using your imagination, and this is one of the things we have to unlock to be able to do this. Architects need to be able to do both of these things. And then you have to ask yourself the question, do I want to be an engineer and live in the linear world where everything's easy and code and logic and I don't have to talk to people? Or do I want to live in the fluffy lateral world? And if you read these two books and see how it feels, you'll get a good sense of which one of these am I. The book, How to Solve It, is linear thinking. It tells you how to solve problems. It should be very familiar to most of you, the techniques that are used in there. The second book is on lateral thinking by De Bono, and it talks about how you can actually train yourself to think outside of these rigid logical structures that you've been taught in your computer science degrees at university. Linear thinking, it turns out that the very best developers are usually excellent linear thinkers, and sometimes when you push them into architecture without preparation, it can be very, very painful because it's a completely different way of looking at the world. But if you go back to the basics and have a look at your philosophical beliefs about the world, then these things become much, much easier. And so the conclusions from this work is that as a software architect, as someone who designs software systems, you already have a philosophy. And you probably didn't decide yourself what that philosophy is. You've absorbed it from your computer science professors, you've absorbed it from the industry around you, you've absorbed it from your company, from your colleagues. It's encapsulated in gut feeling and something called reflective practice, where we learn over time through walking. It's surrounded by marketing, by random ideas, by moonshots. There's a lot of noise and nonsense in there, and we can't tell the difference between what's real and what's not. Learning to understand this and learning how to express this is incredibly important in your development as a software engineer, as an architect. But it's also important to link this back. You have to get things to work. That's still what we get paid for. And so how do we unplug ourselves from this matrix? The way that we do it is to be responsible for your own philosophy of architecture. Don't accept the default that you've been given by the industry and by your education. Question how you fundamentally see things. There's a bunch of reading you can do. I've dropped the names of some philosophers you can look up. Expose yourself to thinking outside of STEM. The humanities graduates are really, really good at this because they've been taught how to think outside of the boundaries that were set for us in our university educations. There's a potential goldmine of new ideas and theories in the heads of every single one of you in this room. If you use these ideas, you can unlock those things. I was able to do it, and I came up with one set of ideas, but every good architect in the industry is capable of doing this with the right philosophical leaning. Read outside of your discipline. And the goal of this is that we should control the model. The model should not control us, which is the lesson, of course, of the Matrix movie. And this is what you'll be able to do if you embrace these ideas. And the final lesson is that it's not the spoon that bends, it's only you. You won't be able to change reality. You won't be able to make these stakeholders smarter. You won't be able to make them give better answers. You won't be able to make them realize that this is a bad idea or this is a good idea. The only thing that can bend is you yourself, and these tools, these ideas, will help you to do that. And I guess where you go from here is up to you. This would have been a good point to have that Matrix music kick in, but copyright is tough, right? And you can find out more about these ideas in this book, or if you have any questions, you can reach me at these places. And so thank you all for coming. It's absolutely incredible that so many developers came to listen to a talk about philosophy. I hope you don't regret it too much. And good luck out there. Thank you.